Okay, I'm going to do the first three kind of tabletop scenario type problems that are in the homework. So this is our first force calculation scenario we've been looking at. So my first problem here, and just before I start that, let me go back through our steps. We're going to draw a free body diagram. We're going to calculate individual forces on our object, and then we're going to figure out how we get net force, and then we can calculate acceleration. Okay, so we're going to go through those steps. So I've got a 50 kilogram box moving at a constant velocity. Everyone should be saying, oh, that is a clue word. That means ultimately my F net is going to be 0. Ooh, make sure you can see this. And my acceleration is going to be 0, because if I'm at a constant velocity, my velocity is not changing, meaning my acceleration is 0, meaning my forces are balanced. I still have forces acting on my object, so we're going to calculate those just for practice. So we're going to have an object. It's moving on a horizontal surface. It is going to have a force of gravity. It is going to have a normal force. These two are equal magnitude, opposite direction. And then I'll have, let's see, I have friction, okay? So I'll just say I've got an applied force and I've got a force of friction, and those are also equal magnitude, opposite direction, because all my forces are balanced, both horizontal or vertically and horizontally, okay? Because I'm just moving at a constant velocity. So individual forces that I can calculate: force of gravity. Remember, that's mass times my acceleration due to gravity. So I've got a 50 kilogram mass. I'm given that times 9.8. Get my trusty calculator here. 50 times 9.8, 490 newtons. I am flat on a tabletop. Okay, my forces here, there's nothing acting at an angle. So my force of gravity equals my normal force in this case, equals 490 newtons. My force of friction, I'm going to do mu, my coefficient of friction, times my normal force. So mu is 0.25. Normal force is 490. So I'm going to do 490 times 0.25. Make sure y'all can kind of see that. 122.5 newtons. And I know that that's also going to be equal to the magnitude of my applied force, because here these two are offsetting each other. So my F nets are going to be 0 vertically, 490 in one direction, 490 in another, and then 0 horizontally, 122.5 in this direction and in this direction. Okay. So my final answers are that these are 0, because I'm moving at a constant velocity. But we got some practice in with these equations, which is good. All right, now we've got another 50 kilogram box, and it's being pushed on a tabletop with an applied force of 200 newtons. And it's got a coefficient of friction, determine F net, and acceleration. So I'm going to assume my box is accelerating across the table, okay? I've got an applied force this time of 200 newtons. So I'm going to draw my free body diagram again. So I've got my forces vertically. My forces horizontally are not going to be balanced. Okay, I'm going to have an F net value. I'm going to go ahead and I'm just going to borrow from my previous problem because it's the same mass, 50 kilograms. So 50 times 9.8 is 490. I'm also going to borrow from that one and reminding myself that, again, here in this case, my force of gravity and normal force are going to be the same. They're just opposite directions. And then my friction force is the same here too. I can borrow that from my previous problem because it's 0.25 times the same normal force, 122.5 newtons. I said my applied force was 200 newtons. That's a given. So my F net is going to be my larger minus my smaller. Remember, we're just taking the absolute value of the force here. So I'm going to have 200. That's my applied force, and that's a given. Minus 122.5. That's my force of friction that I came up with. And we'll see what that is. 200 minus 122.5 is 77.5 newtons. Okay. And then my acceleration is just going to be my F net divided by mass. And that's just from Newton's second law, which I'll write up at the top so we can remember that. So I'm going to have 77.5 divided by 50. I'm running out of room for all my units. 1.55 meters per second. I can do that. Yeah. Okay. Thank you. Sorry. So 1.55 meters per second. All right, last one. We have another 50 kilogram box. This one is slowing down. So we're in this situation, we're going to assume we're not given an applied force. We're given another mu value here, and then that's it. So in this situation, I'm going to have my same box, force of gravity, normal force. I'm assuming that I gave it a push and then it's moving across the tabletop and it's slowing down due to friction. So we're going to be analyzing it as it's slowing down. We're not going to worry about the push or whatever happened to it to get it moving. We're just going to worry about it as it's slowing down. Okay, so our whole net force, if you think about it, is going to be our force of friction value. So I can borrow again from my previous problems because my mass is the same. So my force of gravity is going to be the same. My normal is going to be the same because I'm just on a tabletop, no angles. Force of friction going to be the same because its mu is still 0.25 and normal force is still 490. So I'm going to do 0.25 times 490, I get 122.5 newtons, and that's also equal to my net force because that's my only force acting on my object. Eventually, that's going to slow it down to a stop, okay? But for now, we're just thinking about it as it's moving, as it's in that slowing down stage, what's happening to it. So its acceleration is going to be 122.5 divided by 50. That's my mass. 2.45 newtons. So my object is slowing down by 2.45 meters per second as it's traveling across this tabletop. And eventually it'll slow to a stop. But we're just worried about calculating this rate at which it's slowing down and the net force on it. So all right, hopefully that helps with this first round of problems. The next video, which I'll do probably tomorrow, is going to be on problems at an angle like we did today in class. So there's a couple of those on here. And then we'll move on from there. Thank you for watching.